luminescent property, magnetic, dielectric, thermal, electrical property, all nanophase material has very much affected from those of bulk material. Hence, they plays very important role not only in physics but also in chemistry and material science and technology. What do you mean by phosphors? Phosphors are luminescence materials which convert absorbed energy into electromagnetic radiation. Electromagnetic radiation emitted by luminescent material, it is usually in visible region. Electromagnetic radiation emitted by luminescent material which are visible in visible range. What is the motivation for the problem to study all these things? Oxides are the best host material for the luminescence centers due to their excellent chemical and thermal stability, excellent luminescence in blue, green, and red region of the spectrum. Here, our sample experience in red regions. They have stable crystal structure, high physical and chemical stability, good formability, long persistence time, relatively easy to prepare, multicolor phosphorescence can be obtained, resistance to acids and alkali metals. What do you mean by phosphors? There is a host lattice. Phosphors are basically consists of host materials in which activator ions are incorporated, I mean doped. When the excitation energy incident on the activator, what you call that, the emission will take place. This emission energy converts into visible radiation. I mean, this is invisible radiation. These are the host materials. I mean, yttrium oxide is the host material in which europium is incorporated. To europium, I want to incorporate lithium. It acts as a sensitizer. When the excitation energy incident on the lithium, the energy is transferred to activator ion, that is U3 plus, then the energy is emitted. Excitation energy converts into visible radiation. Yttrium oxide. Yttrium oxide is considered as one of the best host material. Why do you want to consider? It is the best host material for rare earth material, rare earth dopants. They have the excellent properties such as stable crystal structure, high stability, high hardness. Like this, it have so many what you call that physical excellent properties. Hence, we are supposed to what you call that consider yttrium oxide our best host material. There are so many methods to simplify, I mean synthesize the sample. I prefer solution combustion synthesis for to synthesize the sample. Why do you want to consider the solution combustion synthesis? Because combustion synthesis is self and fast, self-propagating, exothermic, less temperature, economic, high yield, and homogeneous. Yttrium oxide is mixed with europium oxide, stoichiometrically calculated lithium oxide, and 1:1 HNO3. It is stirred using mechanical stirrer and which is heated up to 80 degree using a sandbar. A jelly mixture is obtained. To a jelly mixture, a mimosa pedica gel is added to it. It is a green synthesis. Why do you want to add mimosa pedica? Mimosa pedica is a fuel. That is why we want to add. Wow, what is the role of the fuel? It determines morphology, phase, and the properties of the final product. It increases the rate of the reaction and acts as a catalyst, and the mixture of fuel gives out further reduction of particle size. Hence, we want to add mimosa pedica as a what you call that a fuel. Then the mixture is heated to 750 degrees Celsius in a muffle furnace. The final product is obtained. The characterization of this what you call that the final product is done. What are the characterizations we have done? These are the results and discussion. Synthesis and characterization of lithium doped Y2O3 nanophosphors flat panel display devices. These are the highlights. Already I have given the highlights also. What I have given, what I call that, what is the role of fuel? I mean, what are the properties? These are the properties of the fuel. That is, we have used two types of what I call that. We have two types of fuels. We have one is chemical fuel. The other one is biological fuels. We are using biological fuel. There are so many chemical fuels are also there. Urea, citric acid, ODH, like that. Right. This is the role of a fuel. Next, luminescent properties of Y2O3, EO3, Li plus, what you call that, phosphor. This is the phosphor which we have used. Fuel is Mimosa pudica, like that we have used. Next, XRD. This is the XRD graph. Our Y2O3, EO3, Li. I mean, there is a shift. As we go on increasing the concentration of what you call that europium doped Y2O3 Li, there is a major peak, that is 222, which shift towards high energy, higher angle, like this, up to 5 mole, and thereafter it start decreases. It may be due to change in crystal structures. All right. These are the estimated crystal size. See, in what I call that 1 mole, I mean pure yttrium oxide, the size is 20 nanometer, and it varies from 20 nanometer to 14.7 nanometer. However, like this. This is from WH plot that we have not shown here. I mean, these are the what you call that crystal size. This is the WH plot. Sorry. Next, these are the formula which we have used to calculate the crystal size. Next, this is known as what you call that. Sorry. 1 minute. This is known as ritual refinement technique. From this, good of fitness can be calculated. It is found to be 0.96, and the refined lattice parameter is found to be 10.61 Armstrong, and the cell volume is 1197 what you call that Armstrong cube. Confirmed that yttrium oxide was the cubic crystal structure. All right. These are the same images. In 5 mole, in 1 mole concentration, the what you call that same image is found to be conical, and it is also found to be oval shaped nanoparticles, found to be like what you call that the spinning top, found to be like spinning top. Nanobuds. Next, here nanobuds like flower structure we are going to observe. Here a bunch of nanoflowers. It is a bunch of nanoflowers like spring flowers can be observed here in this. Nanoflowers like paddy nature. It is of paddy nature. Right. Next, this is nanoflowers like bunch prismatic tips. Here nanoflowers like bunch of nanofibers. It appears to be like a nanofibers. Next, these are the TEM images. Here we are going to find out what you call that these two are the TEM images. They shows agglomerated nanoparticles consisting of large number of cubic flakes. Here crystal size is found to be 15 to 20 nanometer. It almost matches exactly with the XRD. That is why our sample is what you call that nanoparticle. Next, from here C and D, we are also HR10 we are going to observe, that is 2.35. Now interplanar spacing is found to be 2.513 Armstrong, which is for 211 plane. Right. Here, from this we are explain what you call that our sample is cubic in crystal structure. Right. This is Wood-Tuka plot to find the gap of variation of band gap of EU3 plus concentration, UV visible absorption of Y2O3 EO3 plus Li, 1 to 11 mole nanoparticles, the energy gap is found to be 4.2 to 5.4 electron volt. It is 5.1, oh sorry, 4.1 electron volt to 5.3 electron volt. The band gap is found to be, the energy band gap is found to be vertical. It appears to be in semiconductor in nature. All right. This is just I plotted emission spectra. For the lapse of time, I have given only emission spectra of Y2O3 EU3 plus, which explains the major peaks. Peak is obtained at 612 nanometer for 5 mole concentration of europium doped, lithium co-doped Y2O3 nanophosphors. All right. Chromaticity coordinates CIE and CCT we have explained. That is, this is the CIE gap. Here it is observed like this, and the correlated color temperature is found to be 2600 Kelvin, 2570 Kelvin, and 1868 Kelvin. It is approximately at around 2570 Kelvin. The summary of my the sample which we have synthesis in our lab is the red light emitting cubic Y2O3 EO3 Li nanophosphors 750 degrees Celsius were successfully synthesized by eco-friendly what you call that bio mediated aloe vera gel, I mean mimosa pudica as a reducing agent. The crystal structure, morphology, and luminescent properties are investigated. CIE and CCT is calculated, and it is found to be in within the range of vertical daylight. Thank you, NCPCM, for giving this opportunity, and I should be thankful to the lotus feet of my guide, Dr. H. Nagabhushana sir, and my co-participant, Dr. Ramakrishna, Dr. Malleshappa, and Dr. Nijlingappa sir also. I should be very much thankful to NCPCM for giving this opportunity. Thank you, one and all, sir. Thank you, sir. Thank you, sir.
Prasanna Kumar.
Sir.
One question.
Okay, sir.
What is the role of Li plus with europium in your sample?
What is the role of?
Role of lithium plus with europium.
Sir, it is co-doped, sir. Co-doped.
What you observed in photoluminescence spectra?
In photoluminescence spectra, we want to avoid lithium there, sir. There is no such a role in lithium, but there is a role of europium in what you call that Y2O3 nanophosphors, sir.
But why have you used lithium plus? But so
just for the study purpose, sir.
Study purpose, that will be for growing of some to promote the crystallization or something else.
Yeah, sir. For cubic, yeah, sir.
Okay, or what is the excitation wavelength of in your sample?
612, sir. 612 nanometer.
No, excitation wavelength.
317 nanometer.
UV. Okay.
Yeah, sir.
Okay. Have you compared with another phosphor? You are saying that this is the best phosphor.
Yeah, we prepared many more phosphors, sir. Y2O3 dysprosium is also prepared. Samarium is also prepared, and terbium also prepared, sir. Among all these things, we are not yet compared actually. We have studied all those things. This is the paper we are preparing for the what you call that journal, sir.
Okay. No, but I am asking about yttrium oxide only, about the host material, not the samarium or terbium.
5 mole concentration is the best mole percentage. Best one, sir.
Okay.
Thank you, Sachin, sir. Thank you so much, sir.
Sir, there is one question.
Okay.
Yeah. You are getting the particle size in decreasing order, right? Can you show that slide, please?
Okay, okay, sir.
The,
Yes.
yeah. So it is from 20 nanometer to 14.7 nanometer, right?
Okay, sir.
Yeah. So what is the role of your aloe vera gel here in decreasing the size of this
It is
particle?
just a fuel. Aloe vera gel is just a fuel. It explains the morphology.
Yeah.
It plays a very important role in what you call that morphology, phase properties, and rate of reaction, reduction in what you call that particle size. Okay,
So
no?
there is no effect on the particle side due to the
As
due to that.
the European concentration in stoichiometrically increases,
Yeah.
it may due to the incorporation of European, sir.
Okay.
Okay, sir. Any more questions, sir?
From my side, this is Dr. Irfan. What is the role of surface vector in your samples?
What is the role of
Surface vector as well as strain.
strain?
And surface vector.
I couldn't catch
Because
it.
you show the surface vector is 4.9971 for Y2O3 and decreasing order when you do europium. What is the main role of surface vector in your compositions?
Surface factor. This is not surface structure. It is the surface factor.
Yes, surface vector.
Yeah,
Yes.
surface. Sir, stoichiometrically calculated europium is incorporated to host material. As the host material, what you call that, as the dopant increases, it almost remains same. Surface factor almost remains same. It explains. Okay, no?
Okay.
Thank you. Thank you, Irfan, sir. Any more questions, sir? Any more questions, sir?
Thank you very much, sir. Dr. Prasann Kumar.
Okay, sir.
Now, I invite the next manuscript, 1168.
Shall I quit, sir?
Yes, you may stop sharing now.
Thank you, sir.
One 1168 is ready?
Yes, sir. Yeah, yes, sir. 1 minute. My screen is visible, right?
It's visible. Now you may start, please.
Okay. So, a very good afternoon, everyone. I am Megha Srivastav here to present a paper on Polaron mediated long-lived bandage carriers in lead halide perovskite nanocrystals. Yeah. Yeah.
The screen
Ma'am,
is
your
shown
screen are not
blank.
visible. Please
Start it.
share your screen.
1 minute. So it is visible, right?
Now it's visible.
Okay. So I am Megha Srivastav, presenting here on Polaron mediated long-lived bandedge carriers in lead halide perovskite nanocrystals. To have a structured discussion, I firstly will give a very brief introduction of lead halide perovskite nanocrystals, followed by a discussion on Polaronic carriers in these class of materials, and then I'll be discussing the influence of Polaronic carriers on the ultrafast dynamics, and then I'll conclude my talk. So lead halide perovskite nanocrystals, so these basically consist of two sublattices. The first one being the octahedron sublattice of lead halide, wherein a lead is centered at the and the halide atoms are at the corners of the octahedron. And this is a inorganic lattice, and it is soft and ionic in nature. And due to the soft and ionic nature, this imparts a strong electron-phonon coupling to the system. And second is the sublattice of A cations, where A can either be organic like methylammonium or formamidinium, or it can be an inorganic cation like cesium or rubidium. And here the halide atoms could be any of the halides like chlorine, bromine, or iodine. This soft and ionic lattice, it gives very peculiar properties to the system, like it possesses a long charge diffusion length and long carrier lifetime despite the moderate electron mobility. Also, it possesses a very high defect tolerance despite many structural and dynamic disorders in this system. So what is the reason behind these peculiar properties? So here the key is the Polaron formation in these material. It is neither a free carrier nor a exciton that is basically driving the system. It is basically the Polaron formation in these systems, and that modulates the properties of these systems. So, due to this Polaron formation, these materials have a very potential application in photovoltaic devices. So, here, basically, I first discuss what is a Polaron. So, a Polaron basically is formed from a strong electron-phonon coupling. So, suppose we have a lattice here, and when there is an electron or a carrier inside this lattice, then due to a strong interaction between this electron and the lattice, there forms a Polaron. It polarizes the lattice, and this polarization is transported in the system. So here we are basically studying the Polaron dynamics in FAPBI3 nanocrystals. We have chosen FAPBI3 mainly because it is having a band gap in the which is more beneficial for solar application in solar cells. So here is shown the optical absorption of the FAPBI3 nanocrystals. So here we can see we have actually modified the Elliott equation and modeled the optical absorption, which incorporates the influence of the carrier phonon coupling. In general, the Elliott equation does not include this coupling influence, and here we are including this. So this factor e raised to minus s raised to j by j factorial. This basically is the redistribution of the oscillator strength due to the strong carrier phonon coupling. And this takes into account the concentration of carrier phonon coupling in the system. By modeling the system with this equation, we obtained a band gap at 1.72 and a Polaronic band at 1.69 eV. And by subtracting this 1.69 from 1.72, we obtained a Polaron binding energy of nearly 30 MeV in these systems. Next, to study the ultrafast dynamics, we employ transient absorption spectroscopy, wherein we measure the change in absorption of a broad white light in presence of and absence of pump. So here, basically, the white light is made to fall on a delay generating stage. Red light that is 800 nanometer from an amplifier is made to fall on a delay generated state, and this will in addition to this, there is a 400 nanometer pump coming from the topaz, these two are spatially overlapped onto the sample, and the change in absorption of this white light probe is measured in the presence and absence of pump. So here we have shown the spectral and time evolution of the transient absorption on FePBi3 nanocrystals. So this is the spectral evolution. Here what we could see is we have a bleach at excitonic position, and also there is a photo-induced absorption on the red side of this bleach. So here from this we have shown the spectral evolution, and the corresponding temporal evolution of the bleach and the photo-induced red-shifted absorption is shown in this right-sided figure. Here we can see there are three regions. In first one, there is a simultaneous decay of the absorption and a bleach, and then they both remain constant for a particular time, and thereafter they start decaying. So the simultaneous decay of bleach and PIA, the time of this one is basically regarded as the Polaron formation time. During this time, a Polaron is formed, and for the duration where this is remaining constant is the protection of the carriers due to this Polaron formation. And thereafter, it starts decaying as shown in this region. So here I've shown a schematic for the explanation. So as soon as we excite the sample with the 400 nanometer laser, what will happen? Carriers will be excited to the top of the conduction band, like much above the band gap. And so what will happen? There is an electron-phonon coupling. The carriers will couple with the allo phonons, and also this will lead to the thermalization. So now there are two processes basically. One is the thermalization, and another one is the Polaron formation. So the thermalization will basically result in the relaxation of the carriers to the bandage, and simultaneously there is a formation of Polaron. So here we can see that once the carriers have reached to the bandage, they are protected via phonon dressing. So here by fitting us this bleach dynamics and the absorption dynamics using a single exponential at the initial time scale, we have obtained a time of 0.75 picosecond for as a Polaron formation time. Now, usually what is known in these systems is that this time is similar to the thermalization time. So here I have marked the three regions where we are showing the Polaron formation, Polaron protected bandage carriers, and then the decay. So to measure the thermalization time, the most used method is the by fitting the tail end of the delta A spectrum using a Maxwell-Boltzmann equation. So I have fitted this tail end using this equation, and the extracted carrier temperature is plotted against delay. So what we have obtained is that thermalization time is very much smaller than the this bleach buildup or PIA decay time. So this is very unusual because in general in other semiconductors these times are similar, but here it is not similar, and this can also be regarded to the Polaron formation because here the carriers are not simply free carrier or exciton, they are instead of Polaron, that is a carrier dressed with a lattice disorders. Next, we have performed a fluence dependent transient absorption. So what we have seen is initial dynamics are not changed. That means there is no change in the formation of Polaron time, but at a longer time scale, what we can see is there is a change, like with increase in fluence, the carriers are decaying a little faster. So this faster decay at higher fluence, so this is consistent because due to the overlap of the Polarons. Because the Polarons will overlap due to the high density of the carriers, and due to this overlapping they will be destabilized and will result in the faster decay of the carriers. So these were the studies we have performed, and I will conclude that we have seen a very efficient protection of the bandage carriers for nearly 30 picosecond, and then the carrier slowly decays, and this basically promotes the FePBi3 application in solar cells. And in future, we will be performing the this cation and anion dependent studies, wherein by changing the cation site and the this halide site, or by using the alloying things in the cation and anion site, we can tune the Polaron dynamics in these materials. At at the end, I would like to acknowledge my supervisor, Dr. Adarsh KV, and the NCPCM management and technical team for giving me this opportunity, and also to the funding agencies. So this is my group. Thank you.
Thank you very much. Any questions? Any queries from the participants? Okay, so you can use this lead halide perovskite for photovoltaic applications.
Yes.
So don't you find that lead will be
Hello.
hello?
Yeah. Yes, sir.
Then this lead halide will be used for the photovoltaic application. Then lead will have some toxic effect in the environment.
Right. It is toxic. So there are studies that are going on replacing this lead with tin or some other the material that will be beneficial, and like it won't be more toxic to the environment. But the properties have been more efficient with these this lead halide perovskites only. So there are research going on to replace lead with some other material.
Thank you very much. Now I invite presentation of next manuscript 1169. And I request to all the presenter that they should strictly adhere to the stipulated time of 7 minutes.
Hello, sir. Can you see the screen?
Hi, yes, it's visible.
Okay.
So you start.
Okay. Good afternoon, everyone. I'm Jerry Saji, and I'm from Amrita Vishwavidyapeetham, Kollam, Kerala. I'm going to speak on the analysis of optical band gap and width of Arbic tail. Here, undoped and lithium-doped zinc oxide films were prepared by successive ionic layer absorption and reaction method, that is CLAR method. Zinc oxide material have a wide direct band gap of 3.36 electron volt and a large excitant binding energy of 60 MeV, which makes it a suitable candidate for transparent material over the visible region. In bulk form, ZNO is an insulator, and in two-dimensional form, that is thin film form, it is supposed to be an N-type semiconductor due to the presence of intrinsic defects. The zinc oxide film could be also made P-type by doping with suitable material like lithium. This versatility of getting N-type and P-type from ZNO material makes it a promising candidate for solar cell. And ZNO is also useful in various optoelectronic devices such as optical sensors, light emitter, and so on. Coming to the experimental part, we have taken 0.1 molar concentration of ZNO zinc sulfate solution with the addition of ammonia as the cationic solution, and distilled water at 70 degrees Celsius as taken as anionic solution. The glass substrate were dipped in the cationic solution for 10 seconds to absorb zinc ammonia complex on the surface, and then in the anionic solution for 20 seconds. The deposited films were washed by the mild flow of distilled water. And then the samples were annealed at 500 degrees Celsius for 1 hour to enhance the conversion of zinc hydroxide phase to zinc oxide phase. And doping is done by adding lithium chloride solution into the cationic solution with the atomic weight percentage at 5 atomic weight percentage, 10 atomic weight percentage, and 15 atomic weight percentage. The UV visible transmission and absorption of the film over the wavelength 250 to 900 nanometer were recorded at the UV visible spectra. Results and discussion. These figures show the variation of absorbance with the incident wavelength for the samples. The A is marked as the undoped sample before annealing. AN is undoped sample after annealing. And AN5 is lithium doped sample at 5 ATM, 5 atomic weight percentage. AN10 for 10 atomic weight percentage, and AN15 for 15 atomic weight percentage. The right figure suggested that there is a slight increase in AN, that is annealed sample between the 360 to 380 nanometer range. And the left figure suggested that there is an considerably much big increase in absorbance value for lithium doped AN5 sample when compared to the AN10 and AN15 samples. Here we can see that there is a abrupt variation in the absorbance value over 300 to 400 nanometer, and at a very longer wavelength, 860 to 900 nanometer, there is a abrupt variation. Here the estimated values of extinction coefficient K were plotted against the wavelength for different samples. Here also we can see that the K value of AN5 has higher values when compared to the other samples. And also there is the samples AN10 and AN15 shows a slight increase in extinction coefficient for a wavelength range between 360 and 400 nanometer when compared to the undoped samples. Here we came to calculate the Arbach energy of zinc oxide film, and the Arbach energy is calculated by plotting log alpha against the photon energy. Alpha is the absorption coefficient. And inverse slope of the linear fit drawn at the band edge measures the width of Arbach tail. Here we calculate the band gap of the zinc oxide film, and the band gap is determined from the alpha h nu square to h nu curve. The values of the band gap energy and the width of Arbach tail for different samples are tabulated in the table shown here. And from the table, it is clear that after doping, the width of the Arbach tail is increased considerably, about for 350 range. And also the intrinsic fact is that band gap energy of undoped samples is very high, and it came to about near to the band gap of zinc oxide after doping 5 atomic weight percentage. And the band gap is also increasing after the doping is increased, as you can see in the table. This reported variation in band gap energy and the width of the airbag tail is attributed to the amorphous state and crystal defects in the lattice. The width of the localized state near the band gap increases with increasing doping concentration. Conclusion. The corresponding plots that you have seen, it is suggested that lithium doped zinc oxide film deposited at 5 atomic weight percentage has higher values for all optical parameters calculated when compared to the other samples. The width of the airbag tail was also calculated, and the value suggested that there is a presence of localized state corresponds to the amorphous state of undoped samples. And the width of the tail increases with doping concentration. The band gap energy is also calculated, and it highly depends on the crystal state and doping concentration. These are some of the papers we have used to reference for our paper. Thank you, NCPCM management for giving this opportunity to present our paper, and also I give my gratitude to my mentor, Dr. Ragesh Bamadevan, and my colleague Vaishakar Kumar, without whom this paper cannot be come into life. Thank you.
Mr. Kapil Kumar. Hello. Hello, last presenter, 1169.
Yes, sir.
Can you explain last diagram? I want to know what is the variation of you have observed the Urbach energy with lithium.
Yes, sir.
It is increases or decreases what you observed?
If anyone have any questions, okay, yes, sir. Anyone have any questions? So please ask.
Sir, about the band
if you
gap.
have no.
Yeah.
Sir,
so the next presenter is 117.
Madam,
next presenter.
I am asking one question to Kapil Kumar.
Not Kapil Kumar, this is Jerry Saji. So I am the presenter. Jerry Saji is the presenter. Kapil Kumar.
Okay.
Sir, it is observed that the undoped zinc oxide films has very high range of band gap. It is a very interesting phenomena. But when lithium is doped to 5%, it is decreased to the normal level, about 3.29 EV. And when doping is increased, it is increasing the band gap energy.
Okay.
Thank you, sir. Sir, can I stop the sharing?
Okay. Then next paper ID 1171.
Yes, ma'am.
Please present your paper, ma'am.
Okay. Ma'am, आपकी voice नहीं आ रही. Hello. Hello, ma'am. Hello. Hello. Hello.
Yes, you are audible.
Okay.
Please continue.
Okay. Very good afternoon to all. Myself Nidhi Sharma from Vanasthali Vidyapit, and I'm going to present on performance enhancement of dye synthesized solar cell with broad absorption. So this is the outline of my work, of my presentation. First of all, we'll discuss about the dye synthesized solar cell, then aim of my work, then how we prepare the device, then result discussion. Now, finally, we conclude it. So, introduction. So, in the dye synthesized solar cell, dye plays a very important role in solar energy harnessing and converting into electrical energy. So many organic and metal complex dye have been investigated, in which RU metal complex synthesizer grabbed more attention due to broad absorption. But the cost of metal complex dye is very high. So to reduce the cost, we use the metal-free organic dyes. But the power conversion efficiency of these dyes uh, is limited due to their narrow absorption band. So we use two types of dyes which have complement spectrum, so that we can increase the absorption range of the material. So there are many attempts have been done using mixing of dyes to enhance the performance of solar cell. So in my work, we mixed RU complex dye and organic dye and study the absorption, morphological and electrical properties. So mainly aim of my study is to increase the absorption spectra using RU N71 dye and organic brilliant blue R250 dye. So to increase the absorption, we can increase the efficiency of the dye synthesized solar cell. This is the preparation method, flow chart of my preparation sample. First of all, we prepare the DiO2 film by using Dr. Blade, then we prepare dye. So finally, the device, prepared device have been characterized by UV, VIS, NIR spectroscopy, then FEACM and EDS. Now, finally, the electrical characterization have been done using solar simulator. This is the device structure of dye synthesized solar cell. Now the result discussion, the optical characterization. This graph shows the absorption spectra of mixed dye solution. We know that absorption property of the photoactive material play a main role in deciding the photovoltaic performance of solar cell. But in individual dyes exhibit absorption only a small portion. So we use composition of poses complementary light absorption spectra. Here we use organic and N71 dye in 1:1 ratio, and as expected from the graph we can see the absorption spectra have been has broad range from 400 nanometer to 700 nanometer. It is clear that in sorry it is important in the organic in the dye synthesized solar cell. Now this is the structural and compositional characterization. The image FEACM image demonstrate the uniform distribution of dye synthesized absorbed TiO2 particle dye. एक minute. Which shows the homogeneous distribution of spherical shaped TiO2 nanoparticle. Also, the surface morphology affect the performance of photovoltaic by showing the behavior of absorption and charge transfer. EDS image spectra shows the TiO along with the Ru, which present the N7 dye peak, and sulfur S chlorine sodium, which shows the organic dye peaks, which validate that the dye being composed of mixing of organic and N719. This is the IV characteristic of fabricated dye synthesized solar cell, which is carried out at a room temperature under the illumination condition. So the fabricated DSAC shows the short circuit current value of 2.9 milliampere current, open circuit voltage is 0.86 volt, fill factor is 77.45%, which results in the power conversion efficiency of 7.81%. So the high efficiency can be attributed primarily to the high short circuit current, which is derived from the extended absorption spectrum due to the mixing of these two dyes. Therefore, these results clearly illustrate the benefit of mixing of dyes and also cost effective. Now it is concluded that using two dyes of different absorption range, we can increase the absorption range. So also the morphology present the uniform distribution due to the mixing of these dyes, and it is observed that the high efficiency has mainly resulted wide absorption on the spectrum of mixing dye that can also be correlated with the high short circuit current, which is 2.90. These are some references. Thank you.
Thanks for nice presentation. Now, any question?
Any questions?
Nidhi Sharma.
Hanji, Hanji.
Can you give me the detail about which two dyes you have used?
Yes,
because
sir.
you have used the TiO2 nanoparticle with these dyes.
Yes, sir. N719 metal complex dye, Ru dye. And second is organic brilliant blue R250 dye.
Okay. So you have grown the TiO2 nanoparticle with this dye.
Yes, sir. First of all, we prepared the TiO2 film by using Dr. Blade method. Then we soak into these dyes, mixing of these dyes for 24 hours.
Okay.
Next paper ID is 1172.
Yes, I am present.
Sir, please present your paper.
At first, my previous speaker should answer. Okay. Let me clear my screen. Is it visible now?
Yes, sir.
Okay. So may I start?
Yes, sir, sure.
Okay. Good afternoon, all of you, those who are present and listening to me. This is Dr. Somunath Bera from Amity University, Noida. And this work is mainly part of my PhD students' thesis work. PhD students is Mr. Kaliprasanna Mandap. And the sample and deposition and experiment were performed mainly at UGC DAE CSR Indore, and we have performed also some X-ray scattering measurement at Synchrotron, Germany. So these are the people involved in this work. So mainly we have studied the cobalt AlQ3 bilayer structure. So why we are interested? Wait a minute. Okay, so why we are interested in this material? Because these organic semiconductors have already used in the electronic devices like organic light emitting diode, field effect transistors, solar cell, photovoltaic cell, etc. And these organic semiconductors have an advantage. They are flexible and low cost, and it is easy to fabricate over large surface area. On the other hand, spintronics is a newly developing area where it uses spin degree of carriers like electrons to transfer and manipulate the information. And the spintronics offer low power and high speed electronic devices. So it's already application is in Red Hat in hard disks. Nowadays, a lot of effort is going to combine these two fields. So application of spintronics in organic semiconductor materials. So there are two main advantages of organic semiconductor is that their carrier mobility is very low. Interaction between adjacent molecules are very weak, and energy bands are narrow, and they have a very weak spin orbit coupling. So spin relaxation time is large. So first successful experiment was carried out in 2004 on the vertical organic spin valve. Organic spin valves mean it is consist of two ferromagnetic layers sandwiched between a organic special layer. So this organic special layer should be less than the diffusion length of the organic semiconductor, means about 100 nanometer or less. So horizontal device of making two ferromagnetic layer and in between less than 100 nanometer organic special layer, it's very difficult. So people are mainly working on vertical structure. So you deposit first ferromagnetic layer, then organic special layer on top of a ferromagnetic layer. It's called vertical organic spin valve. But when one try to deposit that vertical organic spin valve structure like shown here, so this is bottom ferromagnetic layer, then organic layer, and then top ferromagnetic layer. When people try to deposit this top ferromagnetic layer, then these ferromagnetic atoms, they penetrate into this soft organic semiconductor layer. So this is called ill-defined organic special layer. So sometimes the device also short-circuited due to this penetration. So our interest to study this interface, ferromagnetic layer on organic semiconductor, and try to reduce this diffusion and try to accurately characterize the how much is the diffusion, how depth is this metal diffusing, how much it is diffusing, and whether we can improve the quality of this interface, means the whether you can reduce the diffusion. So I have already explained about this diffusion. And so what we did before going to deposit the ferromagnetic layer on top of an organic semiconductor, we have studied the structure or quality of the organic semiconductor by depositing at 3 different growth rates. So this is the reflectivity from 3 LQ3 organic semiconductor films deposited at 3 different rates, starting from 5 angstrom per second, B is 2.5 angstrom per second, C is 1 angstrom per second. And we performed the X-ray reflectivity study to determine the thickness of the film, roughness of the film, and the electron density of these ALQ3 materials. And you can, so I have zoomed out this region. You can see this deep shifted towards the right direction, means higher QZ. When we reduce the deposition rate, the electron density of this material, means LQ3 film, increases. Here the electron density profile is shown that for C sample, which was grown at 1 angstrom per second, is larger than the film at 5 angstrom per second. So that means with the reducing the growth rate, we are that density, electron density of this LQ3 film increases. That means there are less porosity or defects in this material. Then we have deposited cobalt film on this, which was LQ3 film, which was deposited at 1 angstrom per second. Another study we have done also, in addition to this reflectivity, we have done grazing incident X-ray, small angle X-ray scattering, and from this vertical strip, you can see the oscillation. From this oscillation, one can determine the film thickness of the LQ3, and from this horizontal strip, one can determine the porosity, pores present in the LQ3 film, how depth it is, and what is its diameter. So this is the data for 3 samples deposited at 3 different deposition rate, and this is the summary. That what we found, that you can see that the electron density increases with decreasing deposition rate, and also you can see that pore distance increases, and also the pore depth decreases. So these two results, independent results, X-ray reflectivity and G-SUX analysis, they are indicating that with the decreasing deposition rate, the quality of the LQ3 films increases. So we have deposited cobalt film on this LQ3 film of different thicknesses, and we found that.
Sorry to interrupt you, sir.
Yes.
Sir, please conclude.
Yes.
Time limit, sir.
1-2 minutes. So we can found that several nanometer of diffusion of this diffusion of cobalt within the LQ3. Then we have done the X-ray standing wave measurement, go further to get the accurate penetration depth, and for 3 samples. So we have simultaneously fitted this reflectivity data and fluorescence from the cobalt, and we found that with the decreasing growth rate, cobalt is diffusing less amount. So this is the fitting parameter, all these results. And in conclusion, what we found, that we have investigated X-ray reflectivity and G-SUX studies to find the quality of the LQ3 film, and we found the suitable deposition rate of LQ3, where we can reduce the diffusion of cobalt into the organic semiconductor LQ3, which plays an important role in the performance of organic spin valve devices. Thanks for listening. Okay, now if you have any question or doubt. Excuse me. If anyone have any doubt or queries, otherwise I will unshare my screen.
Okay. Next paper ID is 1177.
Wait a minute. Yes, I have to unshare it. No?
Yes.
Hello.
Ma'am.
Yeah, my paper ID is 1177. Can I start now?
Yeah, sure, ma'am.
Is my screen visible?
Yes, ma'am.
Okay. Good afternoon, everyone. I'm Adiba, a research scholar from Aligarh Muslim University, and I'm presenting my work done on nickel oxide. The work is done by me and my lab mates. Okay. There has been an increase in research on transition metal oxides. This is due to the fact that they find application in various fields like photovoltaic devices, resistive switching, and etc. We have several candidates available for these applications like zinc oxide, cobalt oxide, copper oxide, nickel oxide, but we have chosen nickel oxide. It is a promising candidate due to its wide band gap and also property varies depending on its morphology. Nickel oxide has a face-centered cubic crystal structure, as we can see from this figure. Oxygen is placed on the corner and face center, while nickel is placed on the edge center. Nickel oxide can have different properties also depending on their synthesis route. We have different synthesis routes available for nickel oxide preparation. What we have used here is Sol-Gel method. It is a cost-effective method, and from the previous available literature, we have concluded that it provides better crystallinity. Therefore, we have used this method. What we did is we prepared a solution of nickel nitrate hexahydrate with deionized water. We prepared another solution of citric acid with deionized water and mixed both the solution and then stirred it at 500 rpm at 80 degrees Celsius. We can see in this figure the liquid has turned slightly green after some stirring. After continuous stirring, a green colored gel was formed, which we left it to dry as such at room temperature overnight, and then we calcinated the obtained sample in furnace. We did not calcinate the whole sample at a given temperature. What we did was we divided the sample into two parts and then calcinated one part at 400 degrees Celsius and another part at 800 degrees Celsius. Now for the structure and morphological property of the sample we got, we performed X-ray diffraction analysis. As we can see from this figure shows XRD result for sample at 400 degrees Celsius. The peaks marked with stars, these and these ones, corresponds to JCPDS card number 471049, and hence they confirm the formation of nickel oxide nanoparticles. We can see there are some different peaks which I have marked with hash. These peaks corresponds to JCPDS card number 897128. They correspond to formation of nickel. Therefore, we concluded that at 400 degrees Celsius, nickel oxide in pure phase is not formed. What we get is nickel oxide with nickel as impurity. This is the graph for calcination at 800 degrees Celsius. As we can see, only peaks corresponding to JCPDS card number 471049 is present. Hence, at 800 degrees Celsius, pure nickel oxide is formed. For finding the crystallite size, we have used Debye-Scherrer formula, which is given by T is equal to K lambda over cos theta, where K is the constant given by 0.9, lambda is the incident wavelength used in XRD measurement, beta is full width at half maxima given by FWHM, and theta is the Bragg's angle. We have also plotted WH plot using the equation beta cos theta is equal to K lambda over D plus 4 epsilon sin theta, where epsilon is the microstrain. This graph is plotted by using the XRD data. We get the value of crystallite size to be 23 nanometer and the value of microstrain to be 0.000367. We can see here we have got a good straight line for WH plot. This means that there is a homogeneous particle size distribution for our data. Also, we can see that for from Debye-Scherrer measurement, we got the value of crystallite size to be 21 nanometer, while from WH plot we get it to be 23 nanometer. This is because Debye-Scherrer does not takes into account the peak broadening that occurs due to strain. It only takes into account the peak broadening that occurs due to size distribution. From whatever analysis we could perform, we conclude that we have formed nickel oxide at 800, pure nickel oxide at 800 degrees Celsius, whereas impure nickel oxide with nickel as impurity at 400 degrees Celsius. There has been some difference in crystallite size by Debye-Scherrer as well as WH plot, and this can be explained by taking into account the strain broadening. And we can conclude that there are different application of nickel oxide nanoparticle, which will be dealt in next paper, which I have not mentioned here. Thank you. Any question?
If anyone have any question, please ask.
Any question?
Okay. Please unshare your screen, ma'am.
Yeah.
Hello.
Yeah, I have concluded.
Ma'am, no one have any question?
Okay.
You can stop. Yeah.
Okay.
Okay. Next paper ID is 1178. Anju Rani. 1178 paper ID. Ma'am, please share your screen.
हमारे इसमें दूसरा फोन बहुत आ रहा है
Is it visible now?
डॉक्टर पवार एक सेकंड सर आपका एक कॉन्फ्रेंस मीटिंग से रिलेटेड कॉल है क्या
Ma'am, you can start.
सर अभी तो मैं अभी एक कॉन्फ्रेंस मीटिंग में आपको थोड़ी देर में कॉल करता हूँ ओके
Good evening to all. I am Anju, research scholar of Maharshi Markandeshwar University, Sadhapur. The topic of this study is cobalt copper co-doped TiO2 nanoparticles for photocatalytic application under visible irradiation. The use of TiO2 for photocatalytic application is limited. First, due to its band gap, which makes it visible, which makes it active only under ultraviolet light, available about 5% of the total solar spectrum, and second, due to rapid recombination of photo-generated electron-hole pairs. As a result of a small part of excited carriers can move to the surface of TiO2, which further reduces photocatalytic efficiency. To extend the photocatalytic response to visible region, transition metals are to be doped in TiO2 nanoparticles to restrain electron-hole recombination during migration from inside of the material to the surface. In the present study, we have synthesized cobalt copper co-doped TiO2 nanoparticles by sol gel method, then characterized by following techniques. Example, X-ray diffraction, UV visible spectroscopy, and Fourier transform infrared spectroscopy. The influence of cobalt copper doping on the photocatalytic degradation of Congo red and methyl orange dyes have been investigated under visible light irradiation. For the synthesis of these nanoparticles, we have used cobalt nitrate, cobalt sulfate, pentahydrate, titanium tetraisopropoxide, and methanol. All these chemicals were of AR grade and were purchased from Sigma Aldrich. For synthesis, 0.04 mol% cobalt copper co-doped TiO2, 13 ml of TTIP was added into 50 ml of methanol under constant stirring. After 1 hour, 0.8 ml of nitric acid was added to the as prepared mixture and stirred continuously for 30 minutes. The as obtained solution was named as solution 1. Solution 2 was prepared by dissolving 0.5 gram of cobalt nitrate in small amount of DI water. Then solution 3 was added slowly to the solution 1 under vigorous stirring for 30 minutes at room temperature. The as obtained solution was solution 3. For preparation of solution 4, 0.6 gram of copper sulfate dissolved in small amount of water, and this solution was added slowly to solution 3 to form homogeneous mixture. The resulting mixture was vigorously stirred for 3 hours at room temperature to yield a wet gel. After certain time of aging, obtained precipitates were filtered and washed with DI water to get neutral solution. The gel was dried in oven for 24 hours at 100 degrees Celsius to remove solvents. The dried powder was ground in agate mortar and finally annealed at 400 degrees Celsius for 4 hours to obtain stable nanoparticles. Other concentrations were also prepared by adopting similar procedure by adding appropriate amount of cobalt. In the X-ray spectral, peaks are observed at 3:3 angles, 25.41 degree, 37.95 degree, 48.412 degree, 54.17 degree, 55.19 degree, 62.86 degree, 68.91 degree, 70.41 degree, and 75.26 degree, assigned to 101, 004, 200, 105, 211, 204, 116, and 215, 116, 220, and 215 crystal planes of TiO2. And these are in complete agreement with JCPDS card number 841285 and confirm the formation of anatase phase of TiO2. The crystallite size of the prepared nanoparticles was determined by Debye-Scherrer formula, that is D equal to 0.9 lambda upon beta cos theta. Here value of lambda is 1.5406 angstrom, and this is wavelength of X-rays used. The calculated values of particle size are 16.4 nanometer, 14.9 nanometer, and 13.1 nanometer. The UV visible absorption spectra shows absorption edges in absorption edge is slightly shifted to higher wavelength region on increasing the dopant concentration. This clearly indicates reduction in band gap energy. The band gap energy of synthesized nanoparticles was determined by using relation alpha h mu power 1 by n is equal to b into h mu minus Eg. Here alpha represents optical absorption coefficient, h mu is energy of incident photon, Eg is optical band gap energy, and n is equal to 1 by 2 for indirect transitions occurred in TiO2 semiconductors. The calculated values of band gap energy are found to be 2.87, 2.61, and 1.90. Hello?
Yes, ma'am.
Hello? 1.90
Please continue, ma'am.
electron volt. This means that band gap energy decreases with increase in cobalt content and is attributed to shift in absorption edge towards higher wavelength. In the FTIR spectra, the absorption band observed at 623.15 centimeter inverse corresponds to stretching vibration of TiO in TiO2 network. A low intense absorption band observed at 987.8 centimeter inverse is assigned to TiO, Ti banding vibration in TiO2 anatase. Absorption band observed at 1101.4 centimeter in 1101.4 and 1147.03 centimeter inverse is due to symmetric and asymmetric vibration of COC group. On increasing cobalt concentration, these bands convert into single band. Observed at 1145.10 centimeter inverse is attributed to CO vibration, suggests that cobalt cation effectively enter into TiO2 lattice. The absorption band observed at 1624.53 centimeter inverse in all compositions correspond to the banding vibration of HOH, representing physically absorbed water as moisture. Besides these vibration bands are broad absorption band located at 3376.93 centimeter inverse is attributed to stretching vibration of OH hydroxyl groups and is persistent in all samples under study. Then photocatalytic degradation mechanism. Cobalt
Sorry to
copper
interrupt you, ma'am. Please conclude, ma'am. There is time limit, please.
Okay. From this study, we have concluded that cobalt copper co-doped TiO2 nanoparticles have been successfully repaired by Sol gel technique. The X-ray diffraction confirms the formation of anatase phase of TiO2 nanoparticles. The average particle size and energy band gap found to decrease with increase in dopant concentration. The absorption edge of the prepared sample shift to higher wavelength indicate the reduction in band gap energy. The FTIR spectrum analysis confirms the formation of stable anatase phase of TiO2. The photocatalytic degradation efficiency of prepared samples for degradation of both organic dyes increases with increase in cobalt concentration. These observations suggest that prepared nanoparticles are suitable for photocatalytic application in removal of Congo red and methyl orange dyes from organic dissolved contaminated water. These are references. Thank you.
If anyone have any question, please ask. If anyone have any query. So the next presenter is 1184.
Hello, ma'am. Hello. Am I audible? Hello, ma'am.
Yeah, you're audible.
Shall I share my screen?
Yeah, sure.
Okay, thank you. Good afternoon, everyone. Myself, Parvati, from School of Pure and Applied Physics, Mahatma Gandhi University, Kottayam, Kerala. First of all, I would like to thank the conference organizers for giving me an opportunity to present my work here. The title of my presentation is Gold Graphene Oxide Nanohybrids as source platforms fabricated via pulse laser ablation. So I would like to start with an introduction about laser ablation and laser plasma. Actually, laser ablation is a mass removal of material by coupling laser energy to a target. It can be done both in air and liquid, ambient liquid. Compared to the laser ablation in air, the liquid phase laser ablation is better because when we are ablating materials in air medium, then there is a chance of contamination of the atmosphere due to the aerosols. Due to the presence of aerosols, it will be very hazardous to the researchers, and also laser synthesis of colloids in liquid phases better compared to the air. So in the liquid phase laser ablation, there is photonics is there, nanotechnology is there, plasma is there. So it is altogether, it is an interdisciplinary topic which includes physics, chemistry, and subdisciplines like photochemistry, fluid mechanics, plasma spectroscopy, laser physics, sonochemistry, etc. In laser ablation, when we are hitting a high intense laser beam onto a material surface, then the electromagnetic field of the laser beam interact with the atoms of the material, and which ejects electrons from the surface of the material, and there is a formation of plasma. Next is the cavitation bubble formation. Actually, this cavitation bubbles cages the nanoparticles, and it will finally release the nanoparticles to the liquid when as the bubble blots out. Next is the methodology of the laser synthesis and processing of colloids. Actually, here we are decorating gold nanoparticles with a graphene sheet using this synthesis protocol. We all know that graphene serves as an outstanding matrix for anchoring numerous nanomaterials because of its atomically thin 2D morphological features. So we have designed a metal graphene nano hybrid through pulse laser ablation. For that, commercially available graphite powder was employed for the preparation of graphene oxide using modified Hummer's method, and a solid thin gold foil was ablated in the aqueous suspension of graphene oxide using second and third harmonic wavelengths of an India laser for the immediate generation of the nanohybrids. So the birth of nanoparticles into an organic solvent is the main crux of this innovation. The laser ablation of a metal target in geosolution is happened here, and this will yield nanoparticles, that is gold nanoparticles, into the geometrics. So this is a unique technology compared to the conventional methods. Compared to the conventional synthesis, laser ablation is absolutely a green synthesis without any chemicals, precursors, and reagents, and which is very fast compared to other synthesis techniques. And it is we can have highly pure nanoparticles through this synthesis way, and there is no byproducts, and this is a one-step simple reaction, and this is very facile and hassle-free technique. And the as prepared nanoparticles or nanostructures or nanohybrids have very high conjugation efficiency, and it have noise reduced surge detection background, and it has higher catalytic activity, etc. So this is the experimental setup and the result and discussion part. Actually, we are focusing on India laser beam, second and third harmonic wavelengths onto a gold foil, which is fixed on the inner walls of a glass cuvette. The cuvette is placed above a magnetic stirrer, and this cuvette is filled with the graphene oxide, as aqueous suspension of graphene oxide. And when we are ablating this target material, gold foil, within microseconds, we can have nanoparticles, gold nanoparticles etched from the surface, and it will anchor onto the graphene oxide sheets. This is the UV visible absorption spectra of the graphene oxide and the hybrid material synthesized at two different laser wavelengths. We can see here we can see that there is a absorption peak of graphene oxide at 234 nanometer, and this is due to the pi star interaction of carbon-carbon bonds, and there is also a shoulder peak at 304 nanometer, and this is due to the n pi star interaction of CO bonds. And we can see that in the hybrid materials, the absorption peak of graphene is slightly shifted to 255 nanometer. That means the graphene is reduced after the ablation, and we can have the signature peaks of gold nanoparticle at 526 nanometers. And this tells us that on the graphene matrix, the gold nanoparticles are highly anchored. And next is the Raman spectra. We can have the confirmed D and G bands here for the geo and the hybrid materials. We can see that the Raman intensity of the hybrid material is higher. That is due to the increased concentration of gold nanoparticles in the hybrid materials. And we can have some other morphological analysis of these hybrid materials. The first one is the hybrid material synthesized at 355 nanometer. Here we can have gold nanoparticle having particle size 550 nanometers, and next one is the graphene hybrid material synthesized at 532 nanometer. Here we can have the particles, gold nanoparticles having particle size 13 nanometer is obtained, and these are all the HR time images having this is the interplanar distance 0.202 nanometers, and this is the SAD pattern showing the crystallinity of the hybrid structures. And these we can use these hybrid structures for surface enhanced Raman scattering, for sensing hazardous materials like dyes and pollutants, etc. Here we can use these hybrid materials for sensing the rhodamin 6G. So we could detect rhodamin 6G very successfully, and the signals having high enhancement. And
Ma'am,
here, yes.
please come to the conclusion, ma'am.
Yes. Okay, okay. We can see that here we can see all the signature peaks of rhodamin here, and the enhancement factor is calculated as 1.24 into 10 to the power of 7, and the LOD is up to 10 to the power of minus 13. And this is the conclusions. We have ablated gold foil NGO, and using second and third harmonic wavelengths of an India laser, we have successfully anchored gold nanoparticles on geosheets. The size, concentration, and stability of this, sorry, it was a typo error. It's gold nanoparticle on geosheets can be easily tuned by the plasma parameters and laser parameters. Plasma parameters means the plasma temperature and plasma electron density, etc. Compared with the previous reported methods, it is a very advantageous due to its simplicity and the absence of chemical contamination, etc. We have developed a well-defined nanohybrid with superior surface enhanced Raman scattering performance for sensing rhodamin, also for MBA, etc. And other applications are in energy storage, catalysis, etc. And I submit my gratitudes towards the conference secretariat, my mentor, Professor Nandakumar Kalarikal, and our Vice Chancellor, Professor Tabu Thomas, and Dr. V. Shivkumaran from IPR Gujarat and PSSI, and for BRNS, DA, and DST for P2 for funding. These are my references, and thank you.
Pravati?
Yes, sir. Yes.
There is a question. What Nd:YAG laser wavelength you have used in experiment? Nd:YAG wavelength?
530. Two wavelengths I have used. They are the second harmonic and third harmonic. Second harmonic is the 532, and third harmonic is 355 nanometer.
Okay. In Raman spectrum, you have found 2 point D and G. So
Yeah,
this is
yes, sir.
graphene or some D and
Sir,
G.
sir, in the Raman spectrum, what do you want to?
You have shown 2 point D and G.
Yes, sir. D and G bands. Yeah.
So this is due to the graphene or mixed with some gold.
This is actually due to the graphene because the D peak is situated at 1349, and the G peak is situated at I think somewhat 1580 per centimeters, and it indicates the existence of defect sites in the graphene layers, and these defects are often assigned to the oxidation of graphite and doping effects in the hexagonal carbon lattice.
Okay, there are so many peaks you have observed from 500 to 2000 in Raman spectrums, surface enhanced spectrums.
Yeah, sir. Yes.
So, what is this interpretation of this?
Oh, okay, sir. I'll tell you, sir. We can see 613, 775, 1184, and all these peaks up to 1650, which is these are the well-defined peaks of rhodamin 6G molecule.
Achha, rhodamin 6G molecules.
In that, the 613, the peak 613 is allotted to the in-plane bending mode of the ring, the graphene ring, and the peak at 77 per centimeter is due to the out-of-plane bending motions of the hydrogen atoms. And the rest of all the peaks is attributed to the aromatic stretching vibrations of the carbon atoms, sir.
Okay.
Okay. Thank you, sir.
Anyone have any questions? Okay, thank you, ma'am. Now next one is 1200. 1200.
Yes, I'm present.
Sir, you
I'm
can.
going to share my screen first.
Yes, sir. Please. You can share your screen.
Is my screen visible now?
Yes, sir, your screen are visible.
Okay, so I would like to, so let me start by thanking the organizing committee for giving me an opportunity to present my work. In this work, I will mainly talk about a PL-based sensor for detection of iron and ferric ions and S2O2 by copper nanoclusters. So as we know that the physical and chemical properties of metals, they greatly depend on size, okay? We change the size and we can see like very interesting parameters. When we reduce the size from bulk to metal nanoparticles, the motion of the electrons, it becomes limited by the size of the nanoparticles. Most of the interactions, they happen at the surface. And these metallic nanoparticles, they display like intense colors due to surface plasmon resonance effect. And we see like, these metal nanoparticles of different colors, they absorb light very strongly. If we further reduce their size, they will change to metal nanoclusters, which we call as a missing link between a single metal ion, a single metal atom, and a plasmonic metal nanoparticle. Now, at this stage, when we reduce the size further from metal nanoparticles to metal nanoclusters, the properties of the particles will disappear, and the energy bands will be like completely discrete. They won't show any behavior of any conduction anymore, and their collective oscillations will be obstructed, and they will not show any SPR effect. But even at that stage, they follow all the quantum mechanical rules, and their interaction with light, we will be able to show some bright luminescence. So a lot of work has been done with gold and silver nanoclusters, but for some regions, copper nanocluster reports on copper nanoclusters are very limited, and there are reasons for that. So as you see the picture on your screen, it was Vacas and Vacas, they actually synthesized copper nanoclusters. And as you go from the extreme left to the right, you see that for n less than 10, these copper nanoclusters, they show a strong fluorescence. But as we cross the number 13, they do not show any fluorescence. So this actually they did with alpha is the amount of the sodium borohydride that they added to basically play with the size of these copper nanoclusters. And now these metal nanoclusters, they have like many interesting applications, from sensing to catalysis to imaging and LED, etc. and etc. What we have done in this work is we have taken copper because it is inexpensive, and we have tried to develop some copper nanoclusters. We have tried to use these bovine serum albumin, a protein, to stabilize these nanoclusters, and then we have tested it for various sensing applications. So the scheme on the screen shows the synthesis of these BSA copper nanoclusters, copper nitrate and L-ascorbic acid in the presence of BSA. So we get basically these BSA cab nanoclusters, and then we have tested these the photoluminescence properties of these BSA capped copper nanoclusters in the presence of ferric ions and S2O2. So the size shape of these BSA copper nanoclusters, they are characterized by TEM, as you can see on the extreme left image. They're spherical in shape and of like extremely small size. The DLS image, the DLS picture in the bottom shows like the hydrodynamic radius is about like few nanometers, like less than 5. The SAD pattern confirms the crystalline structure of these copper nanoclusters. We have also recorded the UV visible spectrum of BSA and BSA capped copper nanoclusters. So the UV of BSA is at 280 nanometers, which is in the black color. It is also present in the BSA capped copper nanoclusters, but we do not see any peak around 560 nanometers, which basically confirms that the coppers are still in the form of nanoclusters and not in the form of nanoparticles. Okay, copper nanoparticles shows a strong absorbance effect at 560 nanometer, which is absent in this graph. We have used well-known photoluminescence spectroscopy for the measurements. So basically, PL is the spontaneous emission of light from a material following optical excitation. So what we have done, if you see the diagram on the extreme right at the bottom, that we have used a different excitation wavelength, and we have tried to find out for which excitation the intensity, the PL intensity is the maximum. We have also checked the performance of these BSA capped copper nanoclusters in the case of different pH. We started with 5 because the isoelectric point of BSA is known to be around 4.7. So if you prepare the samples below that, this will lead to the precipitation of the solution and no PL response will be observed. So, but in the range from 5 to 14, the behavior of these PL, it should basically a linear increase with the increase in the pH. We performed all the experiments around the pH 7. So we started with the S2O2. S2O2 is a very well-known molecule which plays an important role in many biological processes, and hence it is very interesting to know that how much S2O2 is present in, let's say, some food samples or some other samples. Okay, so as you see in this graph that with the increase in the concentration of S2O2 from 0 millimolar to 36 millimolar, the PL intensity, it goes up actually. And as you see on the right hand side of the graph, it shows a plot of 1 minus F naught upon F with respect to the S2O2 concentration, which is basically linear in the range of 0 to 15 millimolar. And from there, we have derived that the detection limit of these BSA capped copper nanoclusters in the for H2O2 is around 0.11 micromolar. We have used the same sensor for the detection of Fe3 plus ions. So as you see in the graph on the left hand side, that the PL intensity in the presence of Fe3 plus ions, it goes down with increase in the concentration. And for around 8 micromolar, the intensity is reduced to almost 70%. And again, by using the standard methods, we have derived the limit of detection, which was found in case of, it's 10 nanomolar, that's a mistake. Okay, it's 10 nanomolar. We have also investigated the effect of the interference of different ions, copper, zinc, sodium, nickel, and etc. So as you see on the left-hand side, the intensity remains more or less the PL intensity of these BSA capped copper nanoclusters. It remains more or less same in the presence of all other ions, while in the presence of Fe3 plus ions, it drastically goes to lower values.
Sir?
Yeah.
Sir, please mind the time limit, sir.
Sorry?
So there is time limit. So please.
Yeah, I'm just going to end it now. Yeah. Okay. So the right side is showed the PL intensity in the presence of different other ions, which shows that okay, for Fe3 plus the intensity is extremely small in comparison to other ions. So with all this, I would like to conclude that we have developed a one-pot environmentally friendly synthesis of copper nanocluster, which was stabilized using BSA. We have tested them for synthesis of for the sensing of Fe3 plus and S2O2 ions. In the case of S2O2, the detection limit was around 0.11 micromolar, and in the case of Fe3 plus, the detection limit was 10 nanomolar. We have even used this method for the detection of Fe3 plus ions in the natural water samples, and these results basically they shows the application of these copper nanoclusters as a multi-responsive PL sensor. And with all this, I would like to thank the committee and everyone who is basically responsible. Thank you very much. Yes, so I think with all this, I'm done. Thank you.
Chandrasekhar.
Yes, sir.
One question: have you fixed the BSA concentration and changed the copper nanocluster for PL measurement?
Actually, so we tried with different concentration of coppers with the fixed BSA, and there wasn't any significant change.
Okay. So what amount you have used for copper nanocluster? About some in mole percent variation, or?
To be exact, I think we fixed in the synthesis where I think the BSA was around 15 milligram per ml, if I remember well. And copper nitrate was probably a few ml, less than 5 actually, less than 5.
Less than 5?
Less than 5, yeah.
ml or millimole?
We followed these ML everywhere. We didn't. I mean, we followed this ML convention everywhere. Probably, yeah. I mean, I don't exactly remember the numbers, to be honest.
Okay. Okay.
Yeah.
Thank you, sir.
Thank you.
Now, next presenter is 1210. 1210.
Okay, stop sharing first. Okay, thank you very much. Okay.
1210. Monica Saxena, ma'am, or Vikas Sharma, sir, or GS Okram, sir. Anyone have here? Okay, sir. Next will be called. Now next is 1213. Next is 1213. Snehalata, ma'am, or Rajesh Kumar, sir. 1213. Now next presenter is 1217. 1217.
Yes.
Sonia Arora, ma'am. Ji. Ma'am, you can present now.
Hello.
Please, ma'am. You can share your screen and start now.
Hello. I'm 1213.
Okay, 1213.
Yeah. Hello.
Okay.
Can I share the screen?
Snehalata, ma'am. Yes, ma'am. Okay. You can.
Okay, ma'am. Just wait. Connection problem. Is it visible? Hello.
Yes, ma'am.
Okay. Thank you, ma'am.
Okay.
Good afternoon, everyone. My presentation topic is to synthesize the tin oxide material with Fe doping. I am research scholar at Sri JJT University, Rajasthan. My NCP CM number is 1213. First of all, I would like to introduce the tin oxide and nanostructured materials. First one is nanostructured materials are continuously applied to improved electrical conductivity and vastly optically transparent properties, have various special characteristics in advanced technology like as optical dynamic machine for non-emissive and emissive information display. Among metal oxide, the nano-sized metal oxides of semiconductor have sensible curiosity due to their extraordinary distinctness in the field of chemical catalysis sensors and optical designers of the applicant. In present scenario, the major attraction of research is toward the fabrication of tin oxide. The tin oxide doped with other metal oxide have optically energetic materials have band gap in the range of visible region. The tin oxide nanoflex have extremely conductive alongside the dominance of the oxides of inorganic materials, that is exceedingly chemically noble and large density. The presence of void at the interstitial positions in the tin oxide directed to exclusive arrangement of the electrical and optical properties. The author is attracted toward the investigation of various properties of tin oxide because of its various functionality and its base application. To increase the functionality and to complete the demand of society, the doping process is broadly used in the present scenario. The guest dopant material are key factors to change their structural parameters like as ABC, which are also called the lattice parameters and also other optical parameters, optical energy band gap, nature of the conductance and the phase. Next is the introduction of newly dopant to its host material not only provide the interesting novel effect but also provide the change in the gain knowledge of the parent atom itself. Thus, we conclude that ultimately outcome of the tin oxide nanostructure materials are correlated with both the synthesis mechanism and the type of constituent particles. It is clear that the optical aspects of nanostructure particles considerably based on their size, and shape, which are essentially calculated by physical factors after the preparation process. However, there are various preparation techniques are existed, but we have adopted the microwave assisted chemical co-precipitation method. First of all, in the chemical procedure, we have used the tin stannic chloride with having formulation SnCl2 2H2O and the ferric nitrate. The solution above prepared appropriate conditions of the ionized H2O under the constant stirring on the magnetic stereo for 2 hours to obtain the clear solution. After that, the ammonium solution was poured into the resultant mixture at 25 degrees Celsius to sustain the value of pH near about to 9 or 10. Then we observe the milky solution, which was stirred continuously for 2 hours. Thereafter, the resulting co-precipitating solution is placed for aging for 1 day. After that, the dull white precipitates were filtered by using the Wortmann filter paper and washed out with water and ethanol solution for number of times to extract the extra contaminants like as chloride and carbonate. And then we get the filtered cake, which was placed in the microwave for 2 shifts for 20 minutes each. And further, a part of sample was placed at different durations of the period and different temperature in the furnace to get the tin oxide in powder form. We have prepared the Fe doped tin oxide for the concentration 5 molar, 10 molar, and 15 molar. Then we have characterized the XRD pattern. XRD pattern was observed, and from the XRD graphs we have studied that there is no change in the main peak of the XRD peak. It might be due to large composition of tin oxide, and there is no actual change in the rutile structure of the tin oxide. The observed pattern show that there is no change in phase of the structure because Fe atom only replaced the tin atom in the crystal. During the preparation, tin oxide on the hydrolysis, SnOH mono is formed and SnOH aggregation provided in the synthesis of nanocrystallite nuclei, and the grain size depend upon the degree of aggregation. Further, we have observed these are the XRD patterns. Figure A shows that these peaks are due to pure tin oxide. Second, B represent the Fe doped 5 concentration, means 5 molar, and C represent the 10 molar, and D represent the 15 concentration. There are various peaks are observed at the having values. These are shown in the slide. Further, we have done the UV visible spectroscopy. The absorption factor elaborate the various factor properties associated with the samples like as oxygen deficiency, band gap, impurity centers, and roughness of the surface. The next is FTIR. FTIR spectroscopy is done in a range of 400 to 4000 centimeter inverse, and there are various peaks are observed. The peak around, I will show. The peak around, mainly we have observed the peaks around 1000 and 500. These two peaks, 750 and 556 are the major peaks. These are shown in this. 652 attributed by SNO2 peak, and the 480 verified by the Fe content is present in a sample. This is also the figure of FTIR of 15% concentration, and this is the photograph of 15, and the previous was of 10%. Thus, we conclude that the XRD and TAM images results or the tin oxide prepared crystal are of with tetragonal rutile structure, and the grain size was reduced with the increasing Fe doping concentration. The variation or turning in the optical band gap with the Fe doping concentration were examined by UV, and further the optical band gap shows the red shift with dopant concentration. From study, we indicate that optical property of pure tin oxide stuff was considerably enhanced with the Fe doping concentration. The presence of Fe in SO2 is confirmed by the FTIR peak, which was at 652 centimeter inverse and 480. Thank you. Is there any question?
Is there any question? Thank you, ma'am.
Thank you.
Now, next is 1217. 1217. Ma'am, you can share your link, share your presentation.
Someone is already sharing.
Hello.
Hello.
Sonia ma'am, you can share your presentation.
हाँ जी मैम. Is my screen is visible?
Yes, ma'am.
Hello. Okay.
Yes,
Myself Sonia Arora. Myself Sonia Arora, and I am the research scholar of JGT University. And my analysis will include the topics introduction, experimental, XRD, FTIR results, and discussion, conclusion, and then references. First of all, there is an introduction about nanotechnology. Nanotechnology just involves the study of technical aspect of materials, which involves the fabrication and manipulation of the materials that have at least one dimension in the nanometer scale, that is in between 1 to 100 nanometers. The properties of nanostructured materials such as sensing, physical, chemical, electrical, and so many optical properties, etc. were changes when brought down to nanoscale. The unexpected change in material behavior is might be due to large surface area in comparison to its volume, and so that there occurs a large enrichment of surface atom at this scale. Among metal oxides, the tin oxide nanostructured material has been promising functional N-type semiconductor substances which possess a wide band gap of 3.6 electron volt at room temperature. SNO2 is a nanostructured material exhibited as rutile structure having lattice constants A and B, which is equivalent to 4.73 angstrom, and C, which is equal to 3.18 angstrom, and is known as cassiterite in its general form. So in present work, the aim of the researcher is to study the cumulative effect of tin oxide and nickel oxide nanostructured materials with change in calcination temperatures. Next is the experimental part. The experimental parts just depicts that the nickel doped tin oxide nanoparticles are synthesized by simple co-precipitation route. These nanoparticles are calcined at different temperatures, that is, at 400 degrees Celsius and 600 degrees Celsius. The characterization of the as synthesized nanomaterials of nickel doped tin oxide was done by XRD and FTIR. The composites of tin oxide and nickel oxide enhanced the properties and possess remarkable behavior. The diffraction peaks were indexed and experimental graph reflected the rutile tetragonal structure of SNO2, which is verified by the JCPDS card number 411445, having lattice constant A and B are equal to 4.73 and C is 3.2 angstrom and space group P42/MnM. XRD reveals that tin oxide with nickel oxide using math software in the X-ray analysis using math software, two matched phases were obtained, such as tin oxide, which is indexed as A, and second one is nickel oxide, which is indexed as B. The observed XRD pattern confirms about the formation of nanocomposite of tin with nickel. The experimental and calculated peaks are well matched, which signifies the formation of nanocomposites. This is the XRD analysis, which is done by using Origin software by plotting y-axis as intensity, and on x-axis there is a variation of angle. First one, the index peak A is 5% concentration of nickel added to the tin at temperature 600 degree for 6 hours. Second one, the red peak, which is indexed as B, is shown in the figure, is at 10% concentration of nickel in tin at temperature 600 for 4 hours. Third one is C, which indicates a 10% concentration of nickel in tin oxide at temperature 600 for 6 hours. This is again the XRD analysis, which is depicted by the math software, which clearly finds that the nickel oxide is purely incorporated in the hot structure of tin oxide. Third one is also XRD analysis by using the MOD software, which evaluates the conformation of peaks, the major peaks that are of tin and nickel. These are the various data that is obtained from these softwares, such as chemical name, mineral name, cassiterite formula, ABC, lattice constants, alpha, beta, gamma, cell volume, number of distinct elements, and many more. Next one are the number of peaks that are present in the sample, that is 28 peaks in range, peaks match, intensity scale, space group. A lot of information is depicted by the two softwares which are given in the table. That is 2 theta, crystallite spacing, intensity, full width, half maximum, so that we can find out the crystal, the size of the crystal. Next one is the FTIR analysis, which is plotted against the transmittance on the y-axis and wave number against the x-axis. This FTIR spectra just reveals that the two peaks, which are around 666 and 624, these are the peaks of metal oxides, which signifies the importance of the composites of metal oxides. And these are the major peaks 3398 and 1633. These are due to the water molecule present in the sample, or somewhat due to the carbon oxide, and somewhat due to the nitrous oxide present in the sample, which are clearly explained in this slide, that the peaks is mainly attributed by metal oxide, the 666 and 624, which have a great significance about the material synthesizing during the process. From FTIR data bank, it was just found that the peak around is due to the SNO2 nanoparticles and is attributed by vibrations between the oxygen, tin and oxygen atoms in SNO2 structure. The second peak is attributed by nickel oxide. So the FTIR data verified that the calcined samples contains both SNO2 and nickel oxide in different phases. Last, we conclude that in present paper, the synthesis mechanism of SNO2 composition with nickel oxide by using a simple co-precipitation technique in a laboratory. The XRD pattern reveals that SNO2 doped nickel oxide sample having nearly the same structure as being the SNO2, that is the tetragonal rutile structure, which proves that nickel atom is incorporated as such in the tin structure. The crystallite size of the sample is determined by using Radley-Scherrer formula by considering the most intense peak, and it is found out that the crystallite size comes out to be 17 to 21 nanometer, the average size of the particle, average crystallite size. The FTI spectra reveal the different peaks of metal oxide corresponds to SNO2 and nickel oxide present in the samples. Lastly, the references which are used in which proves to be very beneficial to making this PPT. Then thank you.
Sonia Arora.
Yes, sir.
What composition you have used for the sample preparation of nickel with SnO2?
So 5% nickel and 95% tin.
5?
Sir, 5% of nickel.
Okay.
5% nickel doping is used, and rest of the material is tin.
SnO2. So have you changed some value of nickel, or it is fixed?
No, sir, it is at 5% or 10%. I have
5
used two concentrations.
5 or 10. Okay.
Okay, thank you, ma'am. Now, next presenter is 1225.
Hey, ma'am.
1225. Yes, sir.
Yes, ma'am.
Sandeep, sir?
Hi, yes, ma'am.
Sir, it's Kapil Kumar Kushwaha. Dr. Kapil Kumar Kushwaha. Okay.
Sir?
So, now you can share your screen. And sir, there is the time limit. So please complete your presentation in between 5 to 6 minutes.
आपने कहा ना मैंने टाइम डिफरेंस किया, आपने टाइम डिफरेंस की स्क्रीन आई थी मैंने जो पढ़ी उसमें 5% था 400 टेम्परेचर पे.
May I be visible, ma'am? Hello. Hello.
Yes, sir. Yes, sir. It is visible.
Okay.
Yes.
Yes, you are visible. You are audible. Continue.
Okay. Good afternoon, one and all. My name is Sandeep Phasate. I am a research student in Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. Now, I will present my paper on the synthesis TGA structural and infrared characterization of BaFe12O19 nanoparticles. The outlines of my talk will be the introduction, synthesis technique, characterization technique, result and discussion, and further conclusion. Now, introduction. The recent rapid development of nanoscience is the result of newfound ability to observe and control the structure at small length and time scale, coupled with the development of computational capability that are most effective at the small scale. Ferrite are the ferromagnetic materials consist of iron oxide and metal oxide. The general formula with the Fe2O4, where the M is the divalent metal ions such as manganese, cobalt, nickel, zinc, etc. Currently, the magnetic catalyst hexagonal ferrite are one of the gifted material due to their magnetic property, capacity to absorb light and chemical stability. A barium hexaferrite with the general formula of BaFe12O19 with the space group of P63 mmC has been widely used as a hard magnetic material for permanent magnet since it was discovered by the Phillips. There are some applications of hexagonal ferrite. The magnetic recording such as magnetic strip on credit cards, microwave communication, microwave darkroom, anti-electromagnetic wave radiation because of its large coercive force due to the magnetocrystalline anisotropy, fine grain structure, and excellent chemical stability. Material synthesis is the most important step in developing the new material. These are some synthesis methods are listed below: co-precipitation method, sol-gel autocombustion method, microemulsion method, hydrothermal method, glass crystallization. Now, the sol-gel method is with the advantage of the chemical route of a lower analysis temperature necessary in the crystallization process, and the crystal growth of particle is easier to control by varying the heat treatment. Therefore, the proposed sample in the nanoparticle dimension will be synthesized by sol-gel autocombustion technique. Now, synthesis of barium hexaferrite by the sol-gel autocombustion method. The AR grade barium nitrate, iron nitrate, and citric acid as a fuel were used as an initial starting material for the sol-gel synthesis process. All these metals, nitrate, were separately dissolved in a minimum amount of deionized water and stirred on a magnetic stirrer for 20 minutes. For the sol, were mixed in a beaker and stirred on a magnetic stirrer until the metal nitrate were completely dissolved and form a clear mixed solution. Then the metal nitrate to the citric acid ratio was taken as 1:3. Then the mixed solution was stirred with the continuous stirring on a magnetic stirrer along with the adding of drop by drop anhydrous ammonia solution to adjust the pH value up to the 7. Then the sol was heated onto the hot plate at the 80 degree centigrade temperature to 5 hours with constant stirring to form a gel. Instantaneously, the gel is ignited with the formation of a large number of gases, and autocombustion process will be the start. This self-ignition high temperature autocombustion result in the lightweight voluminous powder as a product of a reaction. Then the fine powder will be the grinded, and thermal gravitometer analysis TGA of product was performed to understand the phase formation temperature and to determine the final sintering temperature. A loose precursor powder was annihilated at 950 degrees centigrade for 10 hours to obtain the pure barium hexaferrite particle. Then the second characteristic technique, we use the XRD. The X-ray diffraction analysis revealed that all the diffraction peaks seen in the XRD pattern are well matched with the standard pattern of pure barium hexaferrite JCPDS card number 84-0757. This various structural parameters like lattice constant, C by A ratio, unit cell volume, average crystallite size T will be calculated and presented in the given table. After that, the FTIR spectra of the barium hexaferrite nanoparticle analyzed at the 950 degrees centigrade was carried out by the model of Simonov FTIR spectra of BAFE12O19 were recorded in the range of 350 to 4000 centimeter inverse is shown as in a figure. The spectra shows two main absorption bands with the characteristics of the formation of barium hexaferrite. The band around 2900 centimeter inverse related to the stretching vibration of CH band of organic compounds, and the other band at 572 centimeter inverse and 420.85 centimeter inverse are assigned to the stretching vibration band, confirm the presence of the hexagonal ferrite. The band around 2352 centimeter inverse is due to the free CO2 produced from the citric acid. We conclude the barium hexaferrite nanoparticle BAFE12O19 has been successfully synthesized via sol-gel autocombustion method. The X-ray diffraction pattern reveals the formation of M-type hexagonal structure as a prepared BAFE12O19 nanoparticle. The lattice constant A and C are found to be well matched with the standard value. Then the crystallized size of the sample calculated using the device shears formula was obtained in the 47.09 nanometer. The infrared spectra exhibit two distinction absorption band near 420.85 centimeter inverse, 438.14 centimeter inverse, and 572 centimeter inverse, indicating the characteristic feature of hexagonal ferrite. These are some references we used for the paper. Thank you.
Hello, Sandeep.
Hello. Sir.
Is there application of this nanoparticle?
Yes, sir.
What?
We use this hexagonal ferrite at the high density data storage. Another one, magnetic optical recording media.
Okay.
Hello. Sandeep.
Hello. Sir.
Mr. Sandeep, why you have selected sol-gel autocombustion method for your synthesis?
Because of another methods. Sorry, sir. Among the non-conventional wet chemical process of obtain the oxidation material, that sol-gel metal is mostly using this. Again, the appropriate is to cheap and low temperature. Also, the sol-gel method, due to their high chemical homogeneity and low processing temperature. Therefore, we use this method.
One thing, Sandeep. Hello.
Yes, sir.
As you prepare by this sol-gel method, you may also try for glass, as you have mentioned that. Glass
crystallization.
You may also try that.
Okay, thank you, sir. Is there any question, sir?
Okay, you can stop, sir. Next paper ID is 1227.
Hello?
Yes, ma'am.
Yeah, am I audible?
Yes, ma'am.
So I'm starting sharing my screen.
Okay, ma'am. Ma'am, it's not visible.
Yeah, it's
Okay.
not visible. Some trouble in sharing. I don't know why. Is it visible now?
Yes, ma'am.
Myself, Shairi Bishash. I'm a research scholar from IIT ISM Dhanbad. Today I'm going to present my work on annealing time and temperature dependent morphological and optical properties of deep coated TiO2 thin films. I'm not going to any introduction because of the time constraint. I'm straight away going to my deposition system used. In this method, I have prepared titanium dioxide nanocrystallite thin films using hydrothermal assisted sol gel dip coating method. So what I have done here is I have used titanium oxosulfate or titanium sulfate as my precursor, and this is the method by which I have prepared the titanium dioxide sol. And after preparing the titanium dioxide sol, we have deep coated the sol on ITO coated glass substrate using a deep coater unit. And when the films are coated, we have first dried them at 60 degrees centigrade, and later on we have annealed them in a hot air oven. So next, these are the samples I have investigated in this study. We have varied the annealing time and temperature. So as you can see, the sol preparation temperature was 90 degrees centigrade, and for the deep coater system, the number of dipping cycles are at 12, and the substrate or ITO coated glass substrate. Sorry, the substrate is missing here. This is a typological error. So the substrates are ITO coated glass substrate, and the difference we have made in the samples is in the annealing temperature and time. For the first set of samples, the annealing temperatures are kept at 300 degrees centigrade, and annealing time was varied from 4 hours to 8 hours. And for the next batch of samples, we have kept the annealing time fixed at 6 hours, and the annealing temperature are varied from 300 degrees centigrade to 500 degrees centigrade. And we have done the morphological and optical characterizations on these samples. First, we have done XRD. For all the samples, the phase was simply anatase phase. No other phase was found in the samples, and from the XRD data, we have determined the crystallite size using Williamson-Hall plot, and the crystallite size were very small, starting from 7 nanometer to maximum of 16 nanometer. And as we can see here in this table, that as we increase the annealing time or annealing temperature, the crystallite size is increasing. So next, we have done the FSM study to see the morphology of the samples. The morphology of the samples are of granular nature, spherical sphere-like particles, and as we increase the annealing time here, A, B, C are samples made at 4 hours, annealed at 4 hours, 6 hours, and 8 hours. The particle size is increasing a little bit. Actually, these particles are agglomeration of particles. When we saw at a higher magnification image, I have not included the image here, on a higher magnification of image, we could clearly see that these
spherical particles visible here are actually made of teeny, very tiny particles. So these are actually agglomerations. So as we move on from 4 hours to 8 hours, the particle size are increasing, and as we reach 8 hours, besides increment in the particle size, we notice some cracks on the film surface, which can deteriorate the film quality. So for our next batch of samples, we have kept the annealing time fixed at 6 hours and varied the annealing temperature 300 degrees centigrade, 400 degrees centigrade, and 500 degrees centigrade. So as we move on from 300 to 400, the agglomerations are clearly increasing. The size of agglomeration are clearly increasing. But as we move on from 400 degrees centigrade to 500 degrees centigrade, the agglomerations are not that big, or not that the agglomeration size are not that much increasing. The only difference is that some voids has been introduced on the film surface. So next we have gone for the transmission spectra, and the value of transmission was decreased as the annealing time was increased because of the scattering loss at the bigger particle size. And on increasing that annealing time to 8 hours, the transmission is really falling. The value of transmission is really falling. The efficient images showed that the cracks on the film surface, which are responsible for the more scattering loss and decreased transmission spectra. So for the samples annealed at 300 degrees centigrade and 400 degrees centigrade, the transmission nature are similar due to the similar morphology, but at higher annealing temperature, the larger particle agglomerations and interparticle voids are responsible for film roughness, and due to that, due to scattering on the rough surface, the transmission is decreasing. From this transmission value, we have calculated the band gap and Abach energy values for the samples. When sample is annealed for longer time, band gap initially decreases due to rearrangement of crystal in the system, and and Arbach energy value decreases similarly. But later on increasing annealing temperature, band gap decreases as a result of bigger particle size with bigger particle size. But for samples annealed at 400 degrees centigrade and 500 degrees centigrade, the particle size are almost similar. So the band gap values are also very similar. Next, we have calculated the optical constants, the refractive indices, and the extinction coefficient. The value of refractive indices are found to increase as increasing time, and as annealing time and annealing temperature are increased. Similarly, for extinction coefficient, also with increasing annealing time and temperature, the value of extinction coefficient are increased. Next, we have calculated the real and imaginary part of dielectric constants. On increasing annealing time and annealing temperature, the value of real and imaginary part of dielectric constant also increased. To find the level of defect states in the sample, we have carried out the photoluminescence spectroscopy, and as we can see in this figures, that as we increase the annealing time and annealing temperature, the intensity of the photoluminescence peak also increased, which is mostly because of introduction of new kind of defect levels and oxygen vacancies in the film. We have, from this photoluminescence spectroscopy, we have plotted the CRE diagram, and all the samples showed emission in the blue region. And with this, I'm concluding my presentation, saying that all the films prepared by hydrothermal assisted salt gel dip coating method were in anatase phase, All the films are composed of spherical or almost spherical nanoparticles which are attached to each other. As annealing temperature was made to rise, the particle formed bigger agglomerations, and highest transmission value was observed for the samples annealed at least time and lowest temperature. Annealing temperature increased particles tend to agglomerate together, which increased noticeably with annealing time and temperature. Both refractive indices and extinction coefficient increased with the increasing annealing time and temperature. The values of real and imaginary part of dielectric constant are also found to increase with time and temperature. The PL study showed emission in the blue region. And before concluding my talk, I would like to convey my thanks to ACMS IIT Kanpur and Department of Physics IIT ISM Dhanbad for providing us with the XRD facility, CRF IIT ISM Dhanbad for providing us with the EPBI spectroscopy and the efficient facility, DST FIST facility of our department for providing us the photoluminescence spectroscopy, and not last but not the least, my supervisor, Dr. Ashit Kumar Kaur, Associate Professor, Department of Physics, IIT ISM Dhanbad. Thank you. Hello. Is there any question?
I am asking, as you have observed the photoluminescence in blue region.
Yes.
So, is there application?
Yeah, I have not shown it here. We have applied this film for, these films can be applied in desensitized solar cell as well, but we didn't have the facility. So we have applied them in photocatalysis activity. And we got like 60 to 70% degradation after 90 minutes of UV ray irradiation.
Since this blue is very broad,
yes,
so that's why I'm asking.
Yeah, actually, there are many peaks bunched together, so that's why the peaks is very broad, and also in other studies people have got like 90 to 95% of degradation, but we only got around 60 to 70%. So we are trying to improve our films with some other studies, or by doing some other studies actually.
Okay.
Now I would like to invite Dr. K.K. Chaudhary sir for closing the session.
Thank you, and I'm sharing my PPT.
Thank you, ma'am. So, on behalf of organizing committee of NCPCM, I would like to thank our session chair, Dr. Giriraj Sharma from Government PG College, Nimach. I'd also like to extend my thanks to our session judges, Dr. Sachin Kumar Mahajan and Dr. Irfan Mansoori. I would also like to thank the technical coordinators of this session. Without their technical support, the smooth conduct of these sessions were not possible. So I'd like to thank Ms. Disha Harinkhere and Dr. Kapil Kumar Kushwa. Thank you, one and all. Thank you, all the participants, each and everyone. So now I declare completion and closing of this session. Thank you all. Jai Hind.
Thank you, sir. Thank you.
Over and out.